Today we're going to talk about gravity. Gravity is one of the fundamental forces of the universe, and it's an interaction between any two objects that have mass. We've studied it to some extent already near the Earth's surface, but we're going to look at it in more detail. So near the Earth's surface, we usually talk about gravity as just, we talk about an acceleration due to gravity, right? And we call g the free fall acceleration. When I release an apple near the surface of the Earth, it accelerates at 9.8 meters per second squared, approximately. It turns out, though, if I go further and further away from the Earth and I drop the apple, I get slightly different results. So on average, near the Earth's surface, it's about 9.83 meters per second squared. And I go up to the top of Mount Everest, it goes down a little bit. If I go up to 36.6 kilometers above the Earth's surface, it goes down to 9.7. If I go out to like where the space shuttle orbits, the acceleration due to gravity is 8.7. And if I go all the way out to 35,000 kilometers, a communications satellite, the acceleration due to gravity is much, much smaller. So there's a lot going on here. And I'm going to start distinguishing between the free fall acceleration, which is the acceleration that we measure when it goes down, when we release an object. And there's also the acceleration due to gravity. It turns out that g is changed slightly from the acceleration due to gravity. We're going to talk about that a little bit later, but that's the free fall, and that's the acceleration that's entirely due to gravity. So, let's see. In 1687, Sir Isaac Newton, who has revolutionized many other aspects of physics, came up with a theory that explained the interactions between bodies due to gravity. And other people had worked on this, and other people had done bits and pieces, but he was the first person to sort of put it all together and figure it out. So he said that the force of gravity is an attraction between any two particles in the universe, any two objects that have mass, and they attract each other with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In other words, the force between them is some constant times the mass of one times the mass of the other divided by the distance between them squared. So this r is not a radius, it's the distance between them squared. And this constant is the universal gravitational constant, and when you experimentally measure it, you get about 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. So that's the force between any two objects. And for small objects, it's weak. For large objects, it's much stronger. But this is what it looks like, right? The force, the function for the force, is gm1m2 over r squared. And this calculates the force on each of the two objects. So if I have two identical objects, or any two objects, I just multiply their two masses, divided by their distance squared, multiply by g, and I can calculate the force. And the force is the same on either of them. This is sort of a consequence of Newton's third law, right? They exert the exact same equal and opposite force on each other. We're going to treat, if I have two objects that have a certain radius and a size like this, we're going to treat them as point masses like this. We're going to assume that this, something like the Earth or whatever has a large mass and a large radius, but in terms of its distance to another object, it's the distance of its center of mass. So we treat it as a point mass. So these two objects here, they exert a force on each other, and the distance between them is the distance between their centers, right? Not the distance between the ends. And so the force is calculated. We can treat them as a point mass, and we can calculate the force between these two objects rather easily. So here's an example of calculating a force between Earth and the Moon. So remember, there's going to be a force on the Earth that's going to be attractive to the Moon, and there's going to be the exact same force on the Moon in this direction. And we can calculate that force. So I've given you all the information you need here, right? There's the gravitational constant, there's the mass of the Earth, there's the mass of the Moon. Mass of the Earth is 5.972 times 10 to the 24 kilograms. The mass of the Moon is 7.348 times 10 to the 22 kilograms. The average distance between the Earth and the Moon, it changes a little bit over time. We'll get to that later. It's about 3.84 times 10 to the 8 meters. So they're pretty far from each other. So we can calculate the average force between them. So we would just plug in everything into, it would be g times the mass of the Earth times the mass of the Moon over the distance between them, which is re Moon, squared. So let's plug in all those numbers. So g, of course, is 6.674 times 10 to the minus 11 newtons meters squared over kilograms squared. I have g, and we're going to plug in the mass of the Earth, which here we're using 5.972 times 10 to the 24 kilograms. And then there's also the mass of the Moon, 7.348 times 10 to the 22 kilograms, and divided by the distance between them squared, which is 7.348 times 10 to the 22, oops, wrong numbers. The distance between them is given as 3.844 times 10 to the 8 meters squared. And you see here that these meters are square. They're going to cancel out that. These 2 kilograms are going to cancel out those 2 kilograms, and I'm going to be left with newtons. And when I plug in everything, I get approximately 1.982 times 10 to the 20 newtons. So that's the force that they exert each other. They exert the exact same equal and opposite force on each other. And if I wanted to, I could calculate the acceleration for each one, right? So for the Earth, I can calculate the acceleration. I just use the force is equal to the mass of Earth times the acceleration of Earth. So that gives me the acceleration of Earth. It's equal to force over mass of Earth. And that gives me a value of about 3.319 times 10 to the minus 5 meters per second squared. And when I do the same thing for the Moon, right, I would say the acceleration of the Moon would be the force divided by the mass of the Moon. I'm dividing it by a much smaller value. So the acceleration of the Moon will be 2.697 times 10 to the minus 3 meters per second squared. So the Moon is feeling a stronger acceleration, even though they have the same force, right? Because the Moon has less mass, it feels a larger acceleration. So let's compare a few different situations here. So starting with these two masses, m, a distance d apart. If I sort of plug in the values into this equation for the force, right, the force ends up being g times m squared over d squared. So that would be the force between two identical masses at distance d apart. What if, in this first case, I were to double one of the masses? What effect does that have on the force? Well, let's plug it into the equation, right? So we have g times m from one of the masses times 2m for the other mass over d squared. That ends up being 2g m squared over d squared. So that ends up being twice the force from before. So it's 2 times the force from the first one. So you double one of the masses, you double the force. And that means that both of these will be feeling the same force. Even though we've doubled the mass on one of them, both of them get twice as much force. What if instead we were to plug in half the mass? So in the third case here, we have mass m and one that's half the mass. So as you might expect, you end up with 1/2 g m squared over d squared. So you end up with half of the force. So they would each feel half as much force, something like that. And if you were to double one and double the, so in the fourth case, if you were to double the mass of one and half the mass of the other, they would cancel each other out, and you would just end up with the same force, right? Gm squared over d squared. So you'd end up with the same force. And if you were to change the distance between them, the behavior is slightly different, because the distance depends on, the force, depends on the distance squared. So here, remember, the force is g m squared over d squared. Well, if I were to double the distance, so I have g m squared over 2d squared, so that 2 gets squared, so I end up with 1/4 g m squared over d squared. So in other words, if I double the distance between them, I end up with 1/4 of the force. So this here becomes f over 4, and this here becomes f over 4. Okay, so here, if I were to instead, if I were to instead cut the distance in half, you get the opposite effect. If I cut the distance in half, right, I end up with g m squared over d over 2 squared, and what you end up with is 4 times the force. So we end up with g m squared over d squared, so we end up with 4 times the force. Now, you can combine all these things together that we just saw, right? If compared to the original force, if I were to double the mass of this one, quadruple the mass of that one, and double the distance between them, you can sort of combine all those things together, right? So it would be g times 2 mass for one of them, 4 mass for the other one, all over 2 times the distance squared. So you would end up, when you cancel out all the 2's, you end up with 2 times the force. So you end up with 2 times gm squared over d squared. So 2 times the force. So let's look at a simulation that'll help us see this a little more interactively. So in this example here, you can change the mass of the two objects and change the distance between them. So here we have a 100 kilogram and a 400 kilogram mass that are separated by, it looks like 4 meters. And so here it calculates the force, right? 1.66 times, here let's change to scientific, right? So 1.67 times 10 to the minus 7. And here's 1.67 to the minus 7. So they feel the exact same force. And if I bring them closer together, right? If I cut the distance in half, the force becomes twice as strong, or 4 times stronger. So here again, I cut the distance from 4 to 2, and the force got 4 times stronger. If I go back here, it goes weaker. And if I double the distance, if I change it from 4 to 8, there I get a larger force. And let's move them back to, let's see here, it's 3 meters apart from each other. And if I increase the mass of one of them, the force on both of them increases. If I decrease the mass of this one, the force on both of them decreases. So the force on each of them depends on the mass of both objects, and it depends on the distance between them. So now I'd like to look at an example of, here we have a woman on Earth, and we're going to look at the force between the woman and Earth. Now the best way to do this is to treat them both as point sources. So here's the woman, or point masses, and here's the Earth as a point there. And how far is the woman from the center of mass of the Earth? Well, it will be related to the radius of the Earth, right? And the radius of the Earth is given up there. It's about 6.372 times 10 to the 6 meters. We have, the woman has a mass of 100 kilograms, and the mass of the Earth is significantly larger, 5.972 times 10 to the 24 kilograms. So we can calculate the force between the two of them. So that force is, G, mass of the Earth, mass of the woman, divided by the radius of the Earth squared. And so we get about 9.816 times 10 to the 2 newtons when we calculate that, when we plug in for G and everything. Now, what is the acceleration that the woman feels due to gravity at this point? Assuming there's no normal force, to say it was just the acceleration due to gravity, what would it be? So we would use F equals mass of the woman times the acceleration of the woman. So the acceleration of the woman would be the force divided by the mass of the woman. And we get about 9.816 kilograms meters per, or 9.816 meters per second squared, right? Which is similar to what we usually get for G, the acceleration due to gravity. Now, if we were to do it for Earth, technically she's exerting the exact same force back on Earth, right? So they are exerting the same force on each other. So she's exerting the same force on Earth. What's the force for Earth? Well, what's the acceleration of the Earth? So the acceleration for the Earth will be the force divided by the mass of the Earth. And that's going to be a crazy small number because the mass of the Earth is very large, right? So we have approximately 1.64 times 10 to the minus 27 kilograms. So this is a very, very small acceleration, barely measurable, right? So she will accelerate a lot because much smaller mass than the Earth. Next example. Here we have something similar, but it's the same woman, but on the moon. So here we have the mass of the woman. Here we have the mass of the moon, and we have the distance between the woman and the moon. And when we calculate the force, same way we did before, G, mass of the moon, mass of the woman, over the distance between them, squared, we get a smaller number, 1.625 times 10 to the 2 newtons. And if I was interested in looking at the acceleration of the woman in this case, so in this case the acceleration of the woman will be that force divided by the mass of the woman. Again, and we get approximately 1.625 meters per second squared, which is approximately 1/6 the acceleration due to gravity on Earth. And that's approximately what we measure when we go visit the moon. Next example. Let's say we have just a king right there with a mass of 100 kilograms and a tiger 4 meters away. Technically, let's say they're in outer space, so they're far away from nothing else. So the only thing that interacts with them is they exert a force of gravity on each other. They are going to exert a force of gravity towards each other like that. Okay, so we can calculate what's the distance between them is r is 4 meters. The mass 1 is 100 kilograms. Mass 2 is 100 kilograms. So what's the force that they exert on each other? G m1 m2 over r squared. So it's not very big masses, right? When we calculate it, we get 4.171 times 10 to the minus 8 newtons. That is not a very strong force, right? But that's the force that they exert each other. You're exerting a force on the person 4 meters away from you. Tigers and kings exert forces on each other as well. So what's the acceleration that's going to happen out of this? So the acceleration, since they have the same mass, they will have the same acceleration, right? So it'll be 4.171 divided by 100. So we end up with an acceleration of 4.171 times 10 to the minus 10 meters per second squared. So that is a very, very small acceleration. It would take a long time for those two to fly into each other. So for fun, what we can do is we can ask the question, we're all wondering it, how long would it take for them to reach each other? So if we release them from rest, they will start to move towards each other. So it would be interesting to know, how long does it take for them to reach each other? We can do that. We have all the tools we need. So if they are released from rest, they will accelerate towards each other. Right? So how long until they collide? So just as an approximation, we're just going to treat them as 2-point masses, right? We're going to treat them as 2-point masses. So let's do the calculation. So let's see, how far apart are they from each other? Well, they are a distance of 4 meters from each other. So they have to travel 2 meters before they collide. So let's just assume that they're 2 points like this, and they're going to collide when they've traveled 2 meters. So the distance they are going to travel is 2 meters. Their acceleration, we just calculated it. It's 4.171 times 10 to the minus 10 meters per second squared. How long until they travel those 2 meters and the tiger, I'm guessing, destroys the king? Maybe eats the king. Well, let's use our good old-fashioned kinematics equation. X equals x naught plus v naught t plus 1/2 a t squared. So we're going to assume that v naught is 0. We're going to assume that they start at rest. And so this simplifies, and then we're going to assume that they start at x naught equals 0, right? So we're going to say x naught equals 0. So it starts at the origin, it travels 2 meters. So I end up with x equals 1/2 a t squared, or t is equal to the square root of 2x over a. So if I plug in those numbers, I get about 9,700 roughly 26 seconds, or approximately 27.2 hours. So if you release them after about a day, they will hit each other. Although I'm guessing the tiger will be able to reach him before that, so it'll get messy before 27 hours are up. In this example, we have some object of mass m, and it's split into 2 parts. One part is m minus little m, and the other part is just little m. So if you add these two together, they form the whole. Now it's asking, if I split them up and they're separated by a certain distance, let's call it d, what ratio of little m to big M makes this force between them as strong as possible? So it's asking how much little m do I remove to make this force as large as possible at any given distance f? Well, let's write down the force between them. So the force between them is going to be g times the mass of one, which is m minus m, times the mass of the other, which is little m, divided by d squared. If I multiply things out, I end up with g over d squared times, looks like m minus m squared. So I want to know what value of m is going to make this a maximum force. And so to max min a problem, we just do df dm. We're going to find what value of m is going to make it a maxima or a minima. This ends up being a maxima. So if I take the derivative of that and set it equal to 0, so the derivative of that with respect to m, I'm going to keep everything else constant. So we end up with g over d squared. So the derivative of m times little m is just m, and the derivative of minus m squared is minus 2m equal to 0. So I can get rid of that. So I end up with m minus 2m equals 0. So I end up with m equals 2m, or another way to say it is m is equal to half of m. So in other words, if the mass that is removed is exactly half of the total mass, then I'll get the maximum possible force between those two objects. In this example here, this seems more complicated than it is, but it's meant to highlight that the force in any given object is the sum of all the forces, right? So it's asking what's the net force on the mass in the center of the square. So each of the four other masses are going to exert a force on it, right? But you'll notice that the force on here due to the top left corner is going to be the same as the force here due to the bottom right corner, right? These two are the same. So these two are going to cancel out because it's in both cases it's 2.5 and 5, and it's the same distance. So those two forces are going to cancel out. And the other two forces, there's going to be a force here. Here, let me do a different color. There's going to be a force on this one due to the 3 grams. And there's also going to be a force this way, a weaker force due to the 1 gram, right? So this force here is going to be due to the 1 gram, and this force here is going to be due to the 3 grams. And you can easily convince yourself that those two forces, right, we have, this is due to 3 grams here, right? And this force here is due to 1 gram. So the 1 gram is going to cancel out a fraction of the 3 grams. So this is going to be the same as if there were just one force in this direction due to 2 grams. So I can easily calculate that. I can just calculate the force between, so I'm going to say M1 is the center, and that's 2.50 grams. M2 is our 2 gram mass. And then the distance between them, we have to figure out the distance between them, right? So here's the distance between them. What is that? Well, if this is 20 centimeters, then this is 10 centimeters, and this is 10 centimeters. So that means this here is going to be 10 centimeters plus 10 centimeters square rooted. So 10 squared plus 10 squared, so that's the square root of 200 centimeters. So R is going to be the square root of 10 centimeters squared plus 10 centimeters squared square rooted, so it's square root of 200 centimeters. So now we have everything we need to calculate F. Just plug all this into F, right, which is going to be G M1 M2 over R squared. And when I plug that in, I get a force of about 1.77 times 10 to the minus 20 newtons. Right? The force between small objects like this is not going to be very strong. Forces are usually stronger for gravity between large objects. Now here, if I wanted to calculate the force on some object above the surface of the Earth, of course, you know, if we did before the force of an object on the surface of the Earth, the distance between the object and the center of mass of the Earth is the radius of the Earth. But if I'm a certain height above it, I have to add that a little extra height to calculate the force between that object and the Earth, like for the moon or something orbiting the Earth. So here is the force, G, mass of the Earth, mass of the object, over the distance between them squared. And if you let F equals mg and solve for G, you get the acceleration at different altitudes. And you see that as you go further and further away, the acceleration due to gravity on the Earth gets smaller and smaller. And one way we can represent these forces is with the concept of a field. So near the Earth's surface, we say that there's a gravitational field, okay? Or the Earth creates a gravitational field such that any object near the Earth feels an acceleration due to gravity inwards or downwards. And this is a gravitational field created by Earth. It is, at any point here, there's a acceleration due to gravity inwards towards the center of the Earth. So at every point in space, there's a vector that represents the acceleration due to gravity. So the vector here represents the acceleration due to gravity for a point there. The vector here represents the acceleration due to gravity for a point there. Here's another way of drawing a little bit more clearly, right? We have the vectors near the surface of the Earth are all the same because their distance, the overall distance between the object and the Earth doesn't change much. But here's a vector field further away from Earth. As you get further and further away from the Earth, the acceleration gets smaller and smaller. So this is a vector field, and we're going to spend a lot more time with vector fields when we get to electricity and magnetism next semester. So let's consider now a ball on a string, just to help us remember certain things about centripetal motion. If we have a ball on a rope and spinning it around, and it's moving at a certain speed v, we showed before that the acceleration provided by the rope, we call it the centripetal acceleration, it's just an acceleration provided by the rope, has to be equal to v squared over r. So whatever this distance here is, r, it has to provide that much acceleration for it to move in a circle at a constant speed. And things you can do is you can use the definition of v, it's delta x over delta t. I'm going to solve that for delta t. It's equal to delta x over v. So if I'm interested in how long it takes to go all the way around once, the amount of time is called the period, right? So the period, capital T, is the time for one revolution, for one revolution, or one time all the way to repeat its entire motion. And so how far does it travel? What is the delta x for one full revolution? Well, it's moving in a round circle, so it's going to be 2 pi r, the circumference. Okay, so this is the equation that tells us the period, how long it takes for the ball to go around once. And that's going to come in handy very, very soon. Now, this is to sort of highlight the difference between the acceleration due to gravity and g, which is our free fall acceleration. So let's consider this duck sitting on a scale. Okay. Now, generally, if we just look at the duck and the scale from their frame, the normal force on the duck is equal to the mg downwards. But we're going to look at this from the frame where we're watching the Earth rotate. So you notice here that the Earth is rotating with angular velocity omega. So let's draw a free body diagram here. So here we have the normal force from the scale, and then there's going to be some acceleration downwards, like this. Now, because the duck is moving in a circle, let's assume the duck is on the equator, and because the duck is moving in a circle at a constant speed because of the Earth's rotation, that means it has to have a net centripetal acceleration. You know, we generally treat it as it's not accelerating, because in our reference frame it doesn't feel like we're moving around the Earth, but technically, because the duck is rotating around like this, it feels a centripetal acceleration. So I'm going to say here that the sum of all the forces on the duck are going to be equal to mass times the acceleration, the centripetal acceleration. So the two forces on the duck, right? There's the normal force upwards minus the mass times the acceleration due to gravity, which is slightly different from g, and we'll get to that in a second. And that's going to be equal to, and I'm going to add a minus sign here because we're taking downwards to be negative, and the centripetal acceleration where the duck is going to be downwards. So this is minus m times the centripetal acceleration. Now for the centripetal acceleration, remember there's a requirement. Centripetal acceleration is v squared over r, or if I want to write it in terms of angular velocity, I can write that the centripetal acceleration is also omega squared r, where that's the angular velocity. So we're going to actually use that. So now for n, because in the regular frame we usually say that n is equal to mg, where mg is the free fall acceleration when you release something. So we're going to replace n with mg, which is just what we usually measure as the free fall acceleration. So n is mg minus m acceleration due to gravity equals minus mass times omega squared r. So let's see, we can cancel all these m's here. And what I'd like to do is solve this for g. So let's move things around. So g is going to be equal to acceleration due to gravity minus omega squared r. So the point is that the actual acceleration due to the acceleration that we measure when we drop something and it's in free fall is slightly different than the acceleration due to gravity due to this extra term here. Okay, and so usually, this is roughly 9. Oh, right here. Sorry. The acceleration due to gravity, we calculated it earlier, it's about 9.816 meters per second squared. And if you were to plug in numbers into here, you get about minus 0.0337 meters per second squared. So it's a small enough number that we usually ignore its effect on everything. And to calculate, oh, by the way, to calculate that, I would have to use that omega is approximately delta theta over delta t, where delta theta is 2 pi, and delta t is the time it takes to do one full oscillation, which is 24 hours. And when you do everything there, and you plug it in, you get approximately 7.272 times 10 minus 5 radians per second. But the major point here is that the acceleration due to gravity is the acceleration due to the force of gravity, but the free fall acceleration we measure is usually slightly different because of the reference frame we're in. Quick note, just if you were to imagine that you were inside the Earth, and let's say we removed all the mass inside the Earth here, except for like a thin shell on the outside. So if I'm somewhere inside here, if I were right in the middle of the Earth, let's say, think about what the force would be. The force due to this part would be canceled out from the force due to this part. The force due to that part would be canceled out from the force due to this part. So you can imagine that all the forces on you of gravity, they would actually all cancel out. So the net force on you here would be 0. And you can show that anywhere inside this shell, it would be 0. Here you'd have stronger forces from there, but you have weaker forces from the other parts. And the net force on this person and that force here would be 0. So that's sort of an interesting side effect, is that if you're inside where the matter is, where there is no net gravitational force, all the forces cancel each other out. Another cool thing you could do is imagine you drilled a hole from one end to the other to the Earth. As you're going down, so as I'm going down, when I'm here, I can ignore all the mass outside this shell. And so I would start accelerating downwards like this. So this would be the force, right? It would be like downwards. And when I get to here, the force would be 0. And then when we get to here, the force would start being backwards, something like this. And you would just sort of move back and forth. The object would sort of start there and oscillate back and forth. So if you were to drill a hole through the center of the Earth, and assuming all the other stuff doesn't kill you, you could sort of oscillate back and forth through it. And the interesting thing is that when I'm right here, the only thing that matters for the force of gravity on me at this point is all the mass inside this shell. Everything outside doesn't matter. So a capsule falls from rest through a tunnel, and it would sort of move back and forth between those 2 points.